Any questions? Problems? How many tried? Nobody. Alright, it's going to catch up with you if you don't, because these are, I'm going to go to the next step on this one. Now, some of you had the bounce diagram, but you didn't have this part, and there's some things in here that are a little tricky. So I'm going to ask you, now, did anybody try it at all? No? If you didn't, I'm not going to. I'm here to encourage you, not to condemn you. Last thing I want to do is that. I guess I understand that, but if you have had, especially if you had it before. But what I want to do is go through this, and this is the next step, and this is where they have terminations that are inductive or capacitive. Now, I didn't cover that if you had me the first time around, but this is going to be important. It's important for a lot of reasons. So we're doing bounce diagram stuff again, and I'm going to do at least one of these problems, but I want to cover the terminations where they're not either purely resistive terminations. In other words, something that would look like a CMOS gate, the gateless CMOS thing is capacitive, right? You can also have inductive terminations that have to do with, I guess, in some respect, it can be looked at as the input to a bipolar transistor, but anyway, so what I'm going to do is this. I'm going to start and say that we're going to have just a battery here. We're not going to have a pulse. And this is going to have some value V0. Then I'm going to make the characteristic, or the impedance here, RS equal to Z0. And the reason is it'll prevent any kind of a bounce from the source side. Because it'll get too complicated if I don't do this. Here's my switch at T equals 0. And now, what I'm going to do is put my transmission line here. It has a characteristic of impedance Z0, and there's a phase velocity on this V phase. So that would be probably like the speed of light divided by 5 or something like that, speed of light divided by 2. Then over here, I'm going to put a capacitor. Now, it's just going to have a capacitance C. Now what we're going to take a look at is what happens to the voltage. This would be the load, voltage over here, as a function of P. We're going to assume this thing has a length L. And since I made this Z0, you know that there'll be, the reflection coefficient here will be actually what, 0, correct class? So I'm going to go through this now. Now, first thing I'm going to do is get the reflection coefficient on the source side, and that would be Z0 minus Z0 over the sum 2Z0, which is 0, which is exactly what I want. I don't want any bounce from that source side. And that's more or less typical from what I understand on most logic circuits. By the way, everything we do these days on chip is digital, just about. You have carrier frequencies for radar communications that are actually going to be sinusoidal, but almost everything is digital. It's either, a 1 or a 0, 5 or a 0, and ideally at least. So this really looks like the input gate for a CMOS structure. Now, to be frank about it, really there would be some finite resistance there that's usually very large, but this is good. So now if I come over to this side, I'm going to say, well, this actually has an impedance of 1 over SC. Y'all follow this. This is not in the book. Please be careful, but you can take good notes here and pay attention. I will provide some information on this. I'll put some notes up so you can follow this exactly. Now, the reflection coefficient here, right, this would be at the load end, will be a function of S. And I'm doing it because, frankly, it's easier to understand than a complete time domain solution. Because then I have to write the differential equation there. I have to write that C dV dt was I when you have to solve the whole thing, and it gets a little tedious, I believe. So the reflection coefficient here is the impedance I'm going into, 1 over SC, minus the impedance I came from, Z0, over the impedance I'm going into, plus Z0. Do you all agree with that? Okay? If we're talking about the impedance of the capacitor is 1 over SC. Everybody with me? And you're used to this kind of a discussion, right? You've had signals and systems. Remember, S was equal to J omega plus, or sigma plus J omega. And we're talking about this as well in the S domain rather than in J omega domain. So if we take a look at this right here, we see that the reflection coefficient at the load would be equal to, and I'm going to multiply top and bottom by SC, so I get 1 minus, and then it would be S, and I'm just going to call this TC. Let TC be equal to simply C times Z naught over 1 plus STC. You all follow me on this, class? And again, the only thing I'm doing is going through the definitions. He's had this yesterday, by the way, in my EMC class. So, he's getting it twice. All right, now, when you take a look at this, what I want to do is figure out the voltage here. Now, do you all remember in those bounce diagram models that really the voltage here at the load, it's a superposition of the incoming pulse and the outgoing, or it's 1 plus gamma. That's actually the transmission coefficient. Do you all remember that? 1 plus gamma is the transmission coefficient. So that's what I'm actually after. And that's going to be 1 plus this gamma, the reflection coefficient of the load comes from that. And there's a reason I'm doing this, is because that's what I really care about. When I take that, this value, the transmission coefficient, times the actual voltage that impacts this, that is the voltage developed at the load. It accounts for reflection. So this is going to be equal to 1 plus, and then it's going to be 1 minus STC over 1 plus STC. You all see, the only thing I'm doing here is I'm literally taking the definition of that, putting it there, doing this, okay? Y'all with me? Can you see it okay? All right. Then I come over here and I multiply this, because I want a common denominator. And it's going to be 1 plus STC over 1 minus STC, which is just 1 over 1 plus STC. Y'all follow? Can you see it back there, far back? There's a person. You can see it? Okay. Okay. Now, I'm going to go ahead and say, I'll let this be equal to 1 over TC over 1 over TC plus S. And there's a reason I'm doing that, is because ultimately you can see that I'm going to probably do a partial fraction expansion at some point of this to get the final solution. Y'all follow me? You'll see it in a second. That's just the transmission coefficient. Now, I need to find the value of this voltage V prime that occurs just after that switch closes. Y'all follow me? Remember how to do this? How do we do that? Get that V prime, what do I do? Come over here, take this voltage, right? It's voltage division, isn't it? Simple. It's going to be that voltage, V naught, times the impedance here over the sum of this plus this. It's simple voltage division. So it's V naught over 2Z naught. And that's just V naught over 2 is V prime. Now I did it this way, and again, I selected this to be equal to Z naught to prevent any reflections from this end. That's the only reason I did it this way. It'll simplify the solution. Otherwise, this thing's going to get really kind of messy. So now I take a look at this right here, and I could say that this is actually that times U of T. You all agree with that? In other words, I'm going to eliminate the problem of the switch business, and we're going to just put a U of T there, okay? Now, that takes a certain finite time to get down this length, right? After the switch is closed, and what is we call that? I call it the delay time. That's simply the length of the line, whatever that length is, divided by the velocity of the wave. It's really velocity of the electromagnetic wave on the transmission line. Follow me? Y'all remember me doing this before, right? So there's really only one thing new, and that's this. So now we take a look at that. And that means this V prime will impact here, and the actual signature there would be V prime, or really, I'll call it V naught. I'm probably looking right at it. this equal to, this would be the first way, it would be simply V naught by 2 U of T minus TD. You all agree with that? That would be the voltage waveform as it's propagating down here with the time delay counted for. Okay? Now remember, that's the only one I really care about, because I know anything reflects back here is going to be perfectly transmitted because of the impedance matching condition here. So you don't have to worry about multiple reflections. So I have that waveform coming down, and now I have to make you aware of a few things. So y'all remember back in the day when you had your signals and systems course, probably one of the most important courses you're going to have because you're going to use this stuff throughout your career. One of the things you learned is when you had any function f of t, it had a Fourier transform f of s, right? You all remember that? And f of s was defined as simply the integral from 0 to infinity f of t times e to the minus s t dt. That's just fundamentals. Okay. Now, if you had f of t minus td, I'm not going to prove this, but it's fairly easy to. That simply gave it a time delay, e, or a phase shift here, times f of s. Does everybody remember that? Huh? Can you all see this? Everybody? Okay. Now, when you have u of t, that goes to simply 1 over s, doesn't it? Just to make sure everybody knows, right? And furthermore, u of t minus td would go to e to the minus std times divided by s. You all agree with that? Just make sure that there's nothing here that you don't understand. This should be obvious, but I got to make sure it is. I'm going to come over here, work this part of the board. You know what the problem is. So now, coming over here, just take that much out. I'm going to say that the actual voltage here developed there in the S domain, in the load, is going to be this waveform, but I'm going to transform it. So you see that the u of t minus td right there transforms as e to the minus std divided by s, and it's got the v naught over 2 in front of it. So it's v naught over 2, and then it's going to be times e to the minus std divided by s, and then I have to multiply it by this, the transmission coefficient. Do y'all follow me? All right. Once that wave hits here, I need the transmission coefficient to find the actual waveform here. Everybody okay with that? So I'm going to multiply it by this. Now remember, TC is this right here. It's just Z naught times C. So I have 1 over TC divided by S plus 1 over TC. Everybody okay with that much? All right. Now we'll see where this goes. You could actually write an entire differential equation for this, including the time delays and everything that went on there, and solved it. You could do it with Laplace transforms. It's easier to do it this way. That's the only reason I'm doing it. It's quicker and easier, and it's more intuitive in my opinion. So anytime you have something like this, what do? If we know, I didn't put this here, but there's one other one we know. We know what? E to the minus AT U of T transforms as what? 1 over S plus A. We know that one too. I didn't sort of put that. Right? Those are ones at least you should have some familiarity. When I come over here, I'm going to do a partial fraction expansion. I can see I have 2 poles. I have 1 over S and 1 over S plus TC. So the first pole is just A over S. Second pole, and I'll tell you what, I'm going to even ignore this part. What I'm going to do is this. Before I do this one, I'm going to ignore this e to the minus std, because I know that's just going to be a time delay operator, like whatever the solution I get. So I'll take v naught over 2, and then I'm going to take 1 over tc here, and then I have 1 over s times 1 over s plus 1 over tc. And I'm going to expand that to partial fraction. So I'm going to take this, and it's going to be A over S plus B over S plus 1 over TC. Okay, I'm gonna stop for a second, just gather your thoughts, you understand where I'm going with this. Once I have that partial fraction expansion done, I know that I can go back to the time domain very easily, because these are well-known transform pairs. Y'all follow? Okay? So let's do this. How do I get A? Do you remember how to get A? Anybody? This is the way I discuss this with everybody. That pole occurs at S equals 0, right? So multiply both sides by S. I'm only going to do this once. And then multiplying by S gets rid of that, right? Now, once you do that, then you observe what the condition is when S equals 0. When S equals 0, this goes away. Does everybody see that? If S equals 0 goes away, and I'm left with this, and at S equals 0, you can see what happens. I have 1 over TC times TC, or 1 times V naught, and, did I forget a 2 somewhere? This is a 2. That's my problem. There should be a 2 there. My bad. This 2 here cancels that 2. That's what I should have done. I'm sorry about that. Did you all catch that over there? Because there's 1, there's 2 1s there, that's about it. So when I take a look at this, I cover it up, I see that A right there is simply V naught, isn't it? When S goes to 0, the 1 over TC times TC is 1, I get V naught here. So I can say this is going to be V naught over S. Now I'll put the S back here. There's 1 over S here, so you can see the rest. Now to get B, remember how to get B? This value? What do? They call it the cover-up method, don't they usually? Just cover up that pole on this side, because that's effectively what we do when we multiply both sides by S plus 1 over TC. Then we let S go to minus, right? Minus 1 over TC. When that happens, what do you get? Well, I get 1 over minus 1 over TC times TC, or minus 1 times V naught, or this is simply minus V naught, right there. Everybody follow me on that part? It's not hard to see, just make sure you see it. Now, I know this goes back to the time domain as well. Well, what is this one? U of T, right? So normally it would be just V naught U of T, but if I include this time delay operator into this thing, right? If I go ahead and do that, and then I have this times the time delay operator, then I can see this would be U of T minus TV right there. You all follow me? What's the next one? Minus V naught, right? And it would be what? E to the minus T over TC, right? Time constant? Oh, well, actually it would be what? It would be E to the minus quantity T minus TB because of the time delay over the time constant times U of T minus TB, correct? Does everybody follow that? I mean, you all see it? Just see it. If you got it, let me know. See it? Logan, can you see us okay back there? You guys can see it? All right. Now, what is that really telling you? This is a time domain solution. Well, nothing happens until T equals TD. It's 0. That makes sense, right? But when after that, since we have a capacitor, just think about this. This is a capacitor. And this is really called VL of T, but it's a capacitor. Now, there's one thing about a capacitor. The voltage can't change instantly. The current can, but voltage takes time to build up charge to get a change. You have to accumulate current to build up charge. So, it better be 0 when the event begins. And you can see it is, because when this begins, when T is equal to TD or greater, this is 1, but I have E to the 0, which is 1. So I have V naught minus V naught is 0. It starts at 0, right? And then asymptotically goes to what? Just V naught. So the voltage waveform on this, when you see this, because this is what happens on a gate if you're doing transients on this. So it looks like this. If this is T, and this is VL of t, then at the time delay TD, it's equal to 0, but then it does this, and asymptotically approaches the value V0. And that should make perfect sense to everybody, because if you think about the original problem, where we had a value of plus or minus V0 here, and then we had the switch close. Well, I had a resistor here too, but it won't matter. And the switch close at t equals 0, and then I had this transmission line as such, and I have a capacitor. Now, think about this just for a second. What's really happening when you close that switch after a long period of time? Well, current's going to flow, right? It's going to keep flowing until it develops a voltage that's equal to and opposite V0, and then it stops. So that is the asymptotic value it approaches when you have a capacitor termination. Whitmore's book does talk about this. I'm not sure of the actual way he goes through this part. This is an easier way to see it than writing a differential equation and solving in the time domain with Laplace transforms, in my opinion. Okay? Do you all follow me on that? By the way, if you have his book, it's in chapter 2, and it should be towards the end of that chapter, but I forgot how he does this part. So that's the whole deal when you have a capacitive termination. When you have an inductive termination, it's a little different. But you can almost guess what's going to happen.
What about reflections for this case?
Well, there would be a reflected wave, right? But
I
we
guess it's
didn't
matched at the
That's the
end,
reason I
so
did it,
it's
because we could go ahead. You know, this is one of those problems. At the doctoral level stuff, not at master's, but doctoral level, we go through this where we put an arbitrary impedance, right? A capacitor, inductor, resistor combination on that thing. I actually haven't taught this at the doctoral level, but this is how it's done. Then you take an arbitrary time domain signature, all right? Then you start out by writing a differential equation in the time domain if possible, and then solve it in the time domain, put it in the time domain, then do the Laplace transform of it, then bring it back to partial fraction expansions. Some of those things get tricky, very tricky, especially when you have things that are multiple poles or complex roots. You all remember when you had to do that? How they got to be e to the minus AT times, it would be cosine of some constant, and so it gets to be a bit tedious to do. And for this course, this is actually sufficient to get you started on this thing. So the next thing is inductive terminations. So we're going to go back and have the same deal. And of course, I'm going to make sure RS is equal to Z0. It'd be interesting to go through this thing with just an arbitrary time function. Don't make this condition, and then see what happens. But we're going to find out that those situations get to be really painful. Then I'm going to have my transmission line here. And then I'm going to put an inductor here. Let me check in his book exactly. That is how it does it. Okay, Whitworth does have one where he has it's a steady state. Huh? Now he has a steady state input to that, not a transient, the one I was looking at. You show some of this on page 96, 97, but he's not doing it the way I'm doing it. He doesn't go through the, I don't think he does at least. He's writing a differential equation for that, solving it. Take a look. All right, for this one, again, we're going to have some Z0 here, some phase velocity. The line has a length L. This would have an impedance of SL, and I'm after this. I have a couple of questions, by the way, after this. This is gonna be voltage at the load as a function of P. So, remember how I did the last problem? I went and I first got the reflection coefficient here, and what's that gonna be, guys?
Zero.
That's right. It's zero because it's Z naught minus Z naught over two Z naught is zero. So that's nice. And it doesn't have to be that, but it's gonna be that. Next, I need to find the delay time, and that's simply the length of line divided by the phase velocity. You all agree with that? Then after that, I need to find the reflection coefficient here. And I'm doing it with reflection coefficient before transmission coefficient. So if I want that reflection coefficient at the load as a function of S, what would it be? The impedance I'm going into, which is SL, correct? Minus C naught over SL plus C. Do y'all agree with that? Oh,
We're gonna make like a TL, like we did with TC in the last one.
that's right. You're exactly right. We're gonna get the time constant. Why did I do that, by the way? Well, remember RC circuits? What's the time constant? R times C. What's the time constant there? Z naught times C. Really, an impedance times the capacitance. It's the rate of charge. So, now, I'll go ahead, tell you what, before I do this, I'm gonna get the transmission coefficient, then I'll modify. Well, yeah, I'll do it that way, then I'll modify it. So if you take a look at this, I'll get the transmission coefficient at the load, 1 plus reflection coefficient at the load. So that's gonna be, you look at this, it's going to be 1 plus SL plus or minus C naught over SL plus Z naught. And then over here, it'll be just 1, or SL plus C naught over here. And I have a common denominator. And when you look at this, this is going to be really 2SL divided by SL plus Z naught. Now I'll go get my time constant. Do y'all follow me? When I do that, I find out that this is going to be equal to, I divide top and bottom by L, and I get 2S divided by S plus Z naught over L. Remember what a time constant is for an RL circuit? When it's actually got a current in it, it's actually drop down to zero, it's what? R over L. You okay? So same thing here, Z naught is like an R. That's actually the transmission coefficient of the load. Now I come back here and I say, I need my V prime. By this time, so we'll have, what's V prime going to be, guys? Just want to look at it.
V naught R.
It's V naught times Z naught over Z naught plus Z naught, or V naught over 2, just like the last one, V naught over 2. Now I'm going to go ahead and put the time delay here. This should be times U of T at the sources. At this end, after it transmits down here, it's going to be, the voltage there will be equal to, I'll call this, I'll just use it as V, will be equal to V naught over 2, but then it's going to be U of T minus TD. Correct, class? That's just as before, right? Can everybody follow me on that? Okay, now, at that point, did you have a question? You might, other people may have the same. Go.
For the 2S over S plus Z naught, what is that variable in the denominator?
L.
Is that L?
Yeah. Sorry. I wish my handwriting was better.
Me too.
Everybody wishes my handwriting. All right, you all follow me on that? But really, this should be kind of, if you look at this, every step makes perfect logical sense what I'm doing at that point. Now, come over here. Now, I need to take this and put it into the S domain, right? So what does that go as? Well, the V naught over 2 stays as V naught over 2, right? I have a U of T, but it's got a time delay. What does U of T go to? 1 over S, right? But it's got a time delay, so it's really going to be e to the minus STB over S. Correct? This is just as before. And this should make sense to you. You should have seen this before, this kind of stuff done, and it should make sense what's going on. That's one of the benefits of going through signals and systems. It really helps you go through circuit analysis and everything in the frequency domain without solving differential equations. You're solving algebraic equations. All right, the next thing I do is I say that the actual voltage at the load in the S domain is going to be this transmission coefficient times that voltage right there, I'm calling V. So this is going to be equal to, transmission coefficient is 2S over S plus Z naught over L. Then it's going to be times Z naught over 2, and then it's times 1 over S, and it's times e to the minus STD. Y'all agree? Now here's what I'm going to do. I'm going to ignore this part because I know that's just going to cause a time delay once I get the time domain solution. And I'm going to focus on the time domain solution, the remainder. And I'll do it over here so everybody can see it. Is there something going on today? We're missing quite a few people, but I know it's recorded, so it's probably the reason they're not here. Alright. So, let me do this right now before I take it over. Can you all see this okay? You all see how the 2's cancel right here? I can get rid of those. Alright. You see how the S cancels, the 1 over S and S? So I can get rid of that. So really what I have is that, and that means it's just V naught over S plus Z naught over L. That's the only thing I need to transfer. So if I have V naught over S plus Z naught over L, that one, and I want to transform, what's that going to be, guys? Look over there. E to the minus T over what? Well, it's really T times Z naught over L, right? Right? And then it'll be times U of T. Now that's without the time delay. Then when I put in this, now I have to do the time delay operation. So it would become what? V naught E to the minus quantity T minus TD, right? And it would be, I can divide it by or multiply it by Z naught L. Right? Then it's going to be times U of T minus TD. Do you agree with that? Right. Now that would be the voltage at the load. What does that look like? This is time, this is voltage at the load, right? As a function of time. Nothing happens until what? TD. So that becomes important. Then at TD, what does it do? Instantly, it's got a value of V naught, doesn't it? Right? So it spikes upward, and then it asymptotically goes to 0. You all see that? That's right. The inductor looks like a short at DC or at very long times. Once the transient settles, it's a short circuit. You all follow me? Okay. Now, one thing I didn't ask for in the last one, but if we had this, suppose, the inductor looks like this. We now know the voltage on this inductor as a function of time. What if I wanted the time domain current? How would I get that? What is current related to inductor? What is the one thing you remember? L VI dt is equal to V of T for an inductor, isn't it? Correct? Alright, so if I wanted I, what would I do? I would take 1 over L, right? Then I take the integral from where the event started, TD, to when it ends, which is T. It would have to be for T greater than TD. It would be a V of T prime dt prime, correct? This is my V of T right here. Y'all follow me? You'd integrate that. That's how you would get the value of the current. All right. Now, what do you think that current will go to asymptotically? me make sure I draw the circuit for you over here just a little bit. And just think about this before you answer. Now here's what it's gonna look like for time, as time gets large. This is gonna have a value of Z naught, the switch is closed, and then I would just have, as time goes to infinity, you can ignore the actual transmission line, correct class? What is this current gonna go to? Just take a look. What does this look like? A short circuit, right? Just Z naught over Z naught. It's voltage over Z naught. And that's what the current will go to on this thing. Alright? The current on the other one goes to zero on the capacitor. This capacitor looks like an open circuit. Does this make sense what I showed you today? That's what I planned to do today. I wanted to do at least one problem from homework. There's a really good one. What's the one with the, I put up there where I wanted the current at this load and it was a short circuit? I'm trying to figure out which one it was. Well, we're gonna. It's the one with the short circuit there. Yeah. We're gonna do that. This, because there's one trick here that I didn't cover. Yeah. Okay.
It's a 100-volt source.
Alright, so we got 100 volts.
It's 50 ohms, source resistance.
RS is equal to 50.
Z naught's 100 ohms.
Okay. So here's my transmission line. Z naught is equal to 100 ohms.
B phase is still light.
What's that? Oh, it's still light. Nice. What's the load?
Load
Short.
is short and L is 300.
Alright, so this is 300 volts. Okay. Now, what they want, and what I haven't covered yet, and I don't think this is about the one we're supposed to, is the current at the load as a function of time. It's a short circuit. It's got no voltage. The voltage is zero all the time at the load. Y'all follow me? But you're gonna get a current there. Yeah.
What's the length again?
300 meters.
Okay.
We'll go through this methodically. So, first thing I'm gonna do is get the reflection coefficient here. And that's at the, source end, so what would that be? 50, right? Minus, 100 over 150, so that's minus 1/3. Do you agree with that, everyone? You know, see? Alright, reflection coefficient here is what? Take a look at it. It's 0, right? Minus Z naught over 0 plus Z naught, or minus 1. Follow me? You understand the reason, right? Okay. Keep going on this one. This is minus 1. Okay? Now, if I want the current here, I first have to get the voltage waveform incident on. So I need my V prime as before. So what's V prime going to be? 100, correct? Times what? This is 50, by the way, if you can't read my writing. It would be times what?
100 over 50 plus
100 over 150, right? Because it would be 100 plus 50, correct? So that's 66.667 volts, right? Correct? Everybody with me? Now, it's going to take, did I get the time? No, I didn't. So the time delay is what? That's going to be L over V phase, or it's 300 divided by 3 times 10 to the 8, and that's 1 microsecond, isn't it? Correct, class? So then after that, what happens? Well, you know that when this voltage waveform hits here, I'm just going to talk my way through this one. It's going to hit, and the reflected wave will be the exact same magnitude, only a negative value coming back. Do y'all follow me? They don't hit here. 3 times this reflection coefficient, come back, whack it. and then the negative waveform would go. We can talk about that. Now, if you take a look for a second at the equation so you can appreciate this, when you had V anywhere on a transmission line, that was equal to some V naught plus times e to the minus j beta z plus the reflection coefficient at the load, right there, times e to the plus j beta z. Y'all remember that? That's anywhere on, that's the voltage. So the current, what happens? The current on the transmission line will be V naught plus over Z naught, right? But then it's gonna be what? E to the minus j beta z minus reflection coefficient at the load times e to the j beta z right there. You all follow me? That's a minus reflect. Take a look in there, in your book if you don't believe me. It's a negative sign. And the reason is the waveform's traveling in the opposite direction. And you'll get that. Now, how many remembered that, by the way? Kind of, sort of? All right. Now, what does that mean? Remember, back in the day, this is going to be at z equals 0, because this is where the load is, right here. Z equals 0. All right. Now, take a look at this. The actual waveform, if you're at z equals 0, you get 1 plus the reflection coefficient times V naught is the transmitted voltage. Do you all remember doing that? 1 plus the reflection coefficient was the transmission coefficient, right? Now when you get the current, you're going to get V naught over Z naught. We're going to get that in a second. But then at the load, it's going to be 1 minus the reflection coefficient. Our reflection coefficient is minus 1, so it's 1 minus 1 or 2. The current will double because of that short circuit. Keep that in mind. So now we come down here, and if you look at this, I could do the voltage waveform, but I'm just going to say one thing before I do. Nothing happens until the waveform reaches there after 1 microsecond, right? But after 1 microsecond, what happens? This V prime impact set, so it's going to be V prime divided by Z naught times 2 will give me the value of the current. You all follow me? I'll draw this thing out in a second, but I can tell you what it's going to be. The current right here, or current at the load, will be 0 for 0 greater than, or really for t, how about I do this? T less than 1 microsecond. Then for t greater than 1 microsecond, less than 3 microseconds, because it's 1 microsecond down, then bang 2, bang back 3 microseconds. From there, it's going to be a value of V prime over Z naught times 2 right here. And that's because 1 plus the reflection, 1 minus the reflection coefficient will give me this value. Do you all follow me on that, class? We'll do the thing. That's going to be true for 1 to 3 microseconds. I'll draw up the bounce diagram so you can see this. I think I'm going to do it here, over to this side. Hopefully I have room. So remember when we're drawing bounce diagrams, we come over here. This is time. This is a source side. This is the load side. And normally what you do is partition these things. It's better to do this with engineering paper, that cross-hatch graph paper that you can buy. I think you can still buy that at stores. And each one of these things is TD. So this would be 1 microsecond, 2 microseconds, 3 microseconds, 4 microseconds. You all see that? Now, at t equals 0, this is the voltage bounce side. Come down here, I've got V prime coming here, which is what, 66.667 volts, right? It's here, coming back here, I'm going to have minus 66.667 volts, correct? It's here what happens. It's this times, can somebody give this to me? Times minus 1/3. So take, that's 22 volts, isn't it? 22.22 something. Coming this way?
Yes.
22.22 volts, right? It's here, what's coming back? Minus 22.223. Then coming this way, what do we get? you would take that divided by 3 and get rid of the negative sign. What is that? It's gonna be a small value, but
7.4.
is it 7.4?
7.407.
Okay, now that's the bounce diagram for the current, or for the voltage. I wanna show you the current waveform, how we get it. I'll do it here. So, we're just gonna sketch it. Versus time, this is gonna be 1 microsecond, 2 microseconds, 3 microseconds, 4 microseconds, 5 microseconds, and so forth. So, if this is the current at the load, it's 0 until 1 microsecond goes by. You all follow me? Then I take this voltage, I divide it by Z naught, and I multiply it by 2. Because remember, it's V naught over Z naught. Would be the current waveform coming this way, if you will. And then when it hits here, it's gonna be that current waveform times 1 minus the reflection coefficient of 1 minus a minus of 1 is 1 plus 1, or 2 times that current waveform. So it goes out here, and it's gonna come to a value of, that's gonna be, what is that? 66.667, divided by 100 times 2. I know, 1 point something, anybody? 1.3, 1.2 something? 1.3?
Yes.
1.33 milliamps. Is that right? Is that right? Okay. The answers aren't provided, but I don't remember that off the top of my head. It's gotta be, but it's this value. Yes, 1.33 million. How long does it stay there? Now think about that. The waveform just came in, hit here, right? Now listen,
Why is it milliamps?
Oh,
Because it's just amps.
Oh, sorry, it is amps. My bad. So 1.33 amps. I'm gonna leave it as that. My bad. You're absolutely right. Now we take a look at this. It's here, right? Now the waveform comes down here. It's here. That's 2 microseconds. At 3 microseconds, I have to take this, right? And I'm gonna have to multiply that by, or take that and divide it by Z naught times 2 and add it to that. You all follow me on that? So when I do that, nothing happens until I hit 3 microseconds. Then I take the 1.33 and I add to that the 22.223 by 100 divided by 100 times 2, which is about 0.4. Add that to 1.33 is 1.7 something.
So it's, yeah, it's just gonna be 1.7, it's repeating.
So it goes up to 1.77 amps. Now I'll ask you an obvious question. We could keep going, right? But where's this going? In the long run, what is this going to settle in at? It's just going to be 100 divided by 50 or 2. Can you see it's going to be getting there? And it'll keep on doing that. But that's the bounce diagram. But it's the current in the load. It's not the voltage at the load. Now, if we were talking about the voltage anywhere, like in the middle of the line, we just do it the normal way. Come here, go straight down, at TD over 2 or at a half a microsecond, we go to 66.667 down here, goes to 0 at that point, stays 0 until here, then 22.223, goes to 0 and so forth. So you all follow me? That's how you do that problem. All right, I got done what I wanted to today. All right, for Friday's quiz, it'll be on the stuff we've covered today in the, on Monday's lecture and today's lecture with time domain stuff. All right, so I'll give you the problems, go through them, please. And if you got questions, let me know. Joe, get the project, right? I figure you'll be working on it over Thanksgiving break. It's not that hard, but believe me, don't give yourself one day to do it. Cut yourself some slack, because some of that gets real confused.
So I signed up for